In this video, I'm going to teach you how to figure out the equation that best fits your data, especially when it's a nonlinear function. Let's start by quickly reviewing how you can tell if there's even a correlation between your x and your y variables in your lab. One of the things that can be tricky is sometimes it looks like there's a correlation, like in this graph, it looks like there's a positive correlation of sorts, but there actually isn't, or at least you can't conclude that there is, because all the error bars overlap. If all the error bars overlap, and you can draw a horizontal line through all these error bars, then you can't really say that there's a correlation. Another way to quickly tell is if your maximum gradient is a positive value and your minimum gradient is a negative value, then that means a slope of 0 is a possibility, which means that this is you can't necessarily conclude that there's a correlation between your two data, between your two variables. Now let's review how you know if your graph is linear. If you have a linear function, you should be able to draw a linear trend line, or Excel will draw a best fit linear trend line for you. And as long as your trend line goes through all the error bars of your data points, then it's good. You can call it a linear trend line. Even if your trend does not look linear, like this actually looks curved, okay, but if you can still draw a linear trend line, or if Excel calculates its trend line and it goes through all the error bars, well then that data could actually be represented by this linear trend, and you can go with a linear trend if it's simpler. Sometimes when you don't have, or sometimes when you draw your trend line and it doesn't go through all the error bars, then that means that you most definitely cannot say that the data is linear, and so you've got to figure out what exactly is the equation. That's what we're going to teach you how to do today. So to teach you how to do this, I made up some data for a lab that I made up. Let's say someone was investigating how the radius of a circle or of a ball affects the surface area of that ball or sphere. Okay, so if we took some data, and the data, we measured data, and then we processed our data, and then we come up with this data table here. So here, for this radius, we measured this surface area for the ball, and these are the uncertainties for your different values, and we have 5 different trials and etc., or 5 different radiuses and etc. Then what we want to do is we want to look at this data, and we can see our linear trend line, our best fit line that Excel drew for us, does not actually go through all our error bars. So therefore this linear trend line cannot represent the equation for our data here. So that means that we most likely have unlinear data, or unlinear trend, and we've got to figure out what the shape of this graph really is, what the equation that fits it is. And so there are certain things that we can always look at that will give us an idea, a clue of what it is, because it's really a guess and check game. We're going to guess what the shape is, and then we're going to see if we were right or wrong. So some of the key things that you're going to look at is the shape of the graph, okay? For example, this is a curved up shape, right? There are several functions that look like this, right? You're also going to look at the end behavior, or what you would expect the end behavior to be. For example, if the radius gets bigger and bigger and bigger, the surface area should just get bigger and bigger and bigger continuously, so that keeps on going. Also, look at the expected y and x intercepts. For this, if the radius goes down to 0, I would expect that the surface area should also be 0. So that means that my x and y intercepts should be 0. That's what I would expect to see. So whatever equation I try and fit to my data should meet these general things. It should be a curved up shape. It should have an end behavior where it keeps on going to infinity in both directions, x and y, and it should have a 0, 0 intercept. There are lots of different options for graphs that you can have. You should have printed out the sheet that shows all the different ones, or at least the major ones that we often will see pop up in our classes. Here's just a page of some of those, or at least most of them, including proportional, inverse, nth power, nth root, exponential. Okay, and these are some of even the more common ones out of that list. And we can look and see what this, how this chart works. So for each type of relationship, okay, there's the equation that is listed, the basic parent function equation with a possible vertical stretch of k. And then a power function, which we'll talk about later, a little quick sketch of what the shape looks like, describes their end behavior, the expected y-intercept and x-intercept for this relationship, right? And we do that for each one. And so you can Now, these are all things you should know from Algebra 2, but this is a nice way to remind yourself, and you can just look at the chart if you can't remember those details. So let's take a look and see which one of these actually meets our criteria. So let's see here, which ones has a shape of curved up. So not proportional, not inverse, nth power might work, not nth root, and exponential might work. So just by looking at the shape, we've narrowed it down to two different possible equations, either y equals kx to the power of n, or y equals kn to the power of x, one of those. So let's look at the other things. The end behavior, right? As x goes, x will keep on going out to infinity, and so will y. Exponential, x will go out to infinity, and so will y as well. So they both fit still. The y-intercept, let's see here. The y-intercept for a power function should be 0, 0 unless it was translated, unless the graph is shifted upward or sideways. Well, that fits what we want. Let's see here. For an exponential, the y-intercept should always be your k value, okay? This value right here. And we can see it doesn't actually go through 0, 0. In fact, it should have a horizontal asymptote at y equals 0. As the graph continues on the negative side, it just gets closer and closer and closer to the x-axis and never actually reaches it. We know that's not the case. It should be at 0, 0. So I think the nth power would fit better. Now, I've actually got to decide which power, though, because it could be y equals k to the power of, or x to the power of 2, or 3, or 4, right? It could be a quadratic, or a cubic, or etc. So I've got to decide which one. Thinking about my shape from the graph on the previous slide, it didn't look like it curved too quickly. So if I had to hazard a guess, I'd probably guess that it's a squared function. I'd also probably guess that because I know that surface area, like area in general, usually has to do with squared functions, right? Because you're multiplying your base and your height and things like that. So I would probably guess it would be a quadratic, or x to the power of 2. So on the previous slide, we tried to use our deductive reasoning and our knowledge about what we would expect the function of the graph to look like in order to figure out what the equation, or what we think the equation for the graph would be. Now, from there, what we're going to do is we're going to now learn how to check our graph. However, there's another way to double check before you even do the last step. There's another way, and that's kind of like a cheater method, and it works for a lot of relationships, but not all of them. And that is in Excel, Microsoft Excel. When you graph your data, your nonlinear data, make sure that you do a trend line, insert a trend line, but this time do a power fit, okay? And make sure you display your equation on the chart. And when you do that, when I do that for this particular situation, look at the equation here. It's y is equal to some number times x to the power of, and that's about 2, right? So this is a nice slick trick to figure out what the shape of the equation is because a lot of equations have, or you can be written in a power format. For example, the equation y equals kx can be written as in power format as y equals kx to the power of 1. So if this was actually a linear graph, even though it looks like I thought it was curved or something, but it's truly linear, this power number here should be 1. If it's inverse, right, if it's a graph that looks like this, I would know for sure because the power number for 1 over x is the same as writing x to the power of -1. That's the same as doing inverse. So if this power number came up as -1, that means I've got an inverse relationship, and this is my function. Similarly with powers, right, of 2 or 3, that's quadratic or cubic. And nth roots are fractions. So if you want to do the square root, or root 2, right, that would be 1/2 to the power of 1/2. So if this power number said 0.5, that would mean I have a square root function. Okay, so, or it'd be 1/3 would be cube root, or 1/4 would be quad root. Not all functions work though. For example, an exponential function cannot be written in a power format. Linear can't even be written in a power format. Same with periodic, like sine and cosine and other ones. So like I said, it works for a lot of them. In fact, most relationships will be one of these. However, it doesn't work for all of them. So keep in mind, it is a nice slick trick, but it is not the only way to do it. Now that we know our shape is by the power of 2, we now know the equation, the general shape of the equation is y equals kx squared. Or we can write it in more specific terms according to what we're investigating, right? So our actual y variable now is surface area. So I just replace y with surface area, and I replace the x variable, which is radius, with r. And so now I know that this is the shape of my equation. I figured that out in multiple ways. I did my deductive reasoning, and I did a power fit just to kind of double check. Now the only other thing I need to figure out now is what is this k value. If I can figure out what k is, I've just figured out my equation, and I can then interpret it and write my conclusion. So all I need now is to find k. In order to find k, we need to talk a little bit more about this term called proportional. We said this in class once before, but it's a good review. Proportional means that the ratio of x and y is always constant. To be more specific, if y is proportional to x, remember the symbol alpha means proportional to, kind of like equal sign means that these two are equal, right? So if y is proportional to x, then y divided by x is always equal to some constant k, okay? Or you can rearrange this, move x over here, and y should equal kx, where k is some constant. And k is actually represented on the graph by the slope of this line. So when you have a proportional function, it's easy to figure out what that k value is. You just find the slope of the line. And remember, we're trying to figure out what the k value is in our function. The only problem is, or the only difference is that there's a squared here. So we're going to talk about how do you find k when the function isn't already proportional. And we're going to teach you a trick. It has to do with making it proportional or making it linear. All right, so like we said earlier, y equals kx squared, or the surface area is equal to some value k times r squared, right? That's our equation. We're trying to figure out what k is. In this case, we know that the surface area is not proportional to the radius. So in other words, surface area divided by radius does not equal some constant, right? However, if we look at this equation, we can ask ourselves, what is proportional to surface area? If radius is not proportional to surface area, that doesn't mean nothing is. What surface area divided by what value would give me the constant k? Well, if this is r squared here, and I divide it by both sides, surface area divided by your radius squared, that equals a constant value k. So even though surface area, this number here, or this variable here, and radius are not proportional, this is not a linear graph. If I had graphed it differently, if I had graphed surface area and radius squared, then our graph would be proportional and would be linear. That means that if I create a new graph, surface area and radius squared, the slope of this new graph would be this value constant k, and I would actually know what k is. Let me show you how to do that. Alright, on this slide you can see we have our original data here that's nonlinear. I put the linear trend line back on, but you can see it doesn't go through the error bars and it doesn't fit. That's because surface area is not proportional to radius, remember? So I have my original data table, or my original process data table for this graph as well. So we said we want to make a graph that is proportional. So surface area is not proportional to radius, but surface area is proportional to radius squared. So we're going to create a new graph that graphs surface area and radius squared, and that should be a nice straight line. All right, so in order to do this, I've got to create a new linearized data table. So let's see here. The new y value, instead of being just surface area, actually the y value will still be surface area because I'm going to graph surface area and radius squared. So I just need to copy all my old data from before and my y value variables do not change. I just copy the whole thing down. Okay, same thing. It's my x value variable that's going to be different. Where here I graphed radius, now I'm going to graph radius squared. So I'm going to create a new columns, and this time I'm labeling it radius squared. Notice the units also change. Same with my the title for my error. And I'm going to have to now calculate all these values. How do I do that? Well, this is radius squared, right? Here are my radiuses. I just got to square them. So I do 0.9 times 0.9 and enter it here. And then the next one and the next one, right? And I just square all my radius values and write them out. Now comes the more annoying part. I've now got to figure out the uncertainty in my new x variable, okay, radius squared. My uncertainty before was always the same amount, 0.1. To figure out the uncertainty in this new number, I have to ask myself, is this calculated or measured? It's a calculated quantity because I squared it. And then I say, okay, well, I just got to follow the rules for calculating uncertainties. It's in your pink packet. Go ahead and do so, or review the videos about how to do it. So just a quick summary. When you square, you're supposed to find the percent uncertainty of the original one, and then you just multiply it by 2, and then that is the new percent uncertainty. So I would do 0.1 divided by 0.9. That would be the percent uncertainty, multiply by 2, and then multiply it by this value, and I get my uncertainty. If you need help with that, you can always see your teacher. But in short, after doing those calculations, these would be my correct uncertainties. Now that I've got all my data, I can graph it. And you can see it's already been graphed here. And I've even put my error bars on, and in a minute I'll show you a bigger graph so you can see it. But look, the trend line seems to go through all the error bars, and we'll actually see that it does in a minute. So surface area and radius squared is proportional, even though surface area and just plain old radius is not. The slope of this line right here, the slope of your surface area radius squared graph should be k. So now we've just figured out what k is. K apparently is 12.5. That's what K is. Now here's that same graph, but it's a lot bigger. And I just want you guys to see a little bit better that truly the trend line actually goes through all the error bars. And so we know that this is a good fit. If your trend line did not go through all the error bars on this, what we call your linearized graph, then that means you most likely got the relationship wrong. For example, let's say I thought it was squared and I did all this, and the graph is still a little curved and it doesn't go through all the data points. Well, maybe it's not just r squared, maybe it's r cubed. Maybe I didn't do enough, or I did the wrong thing. Or perhaps I just calculated my data wrong and I need to go back and double check my calculations. But if you graph the new linearized graph and the line does not go through all the error bars, then there's a problem with that, and you've got to figure out why. Either, again, you picked the wrong relationship, and so you have to go through the whole process again, go back to the beginning, decide which maybe it's actually an exponential now, because exponential still has that shape. Maybe we were wrong about the y-intercept. So, and you've got to reason through and figure out what that is. But this fits, so we can keep it. And we now know that surface area, which is our y variable, equals 12.5, or about 12.6, times your x variable, which we now know is radius squared, right? Because that's our x variable on this graph, plus this y-intercept. So I can rewrite the equation, and this is the equation I would use in my conclusion. Surface area is equal to about 12.6 times radius squared plus 4.41. And so this is my new equation that I can use. Let's talk one last thing about interpretation, and make sure that you understand that whenever you finish all this, you've got to interpret your graph, and you've got to interpret the equation. So one of the things you should always talk about in your interpretation is the shape of the graph. We now know, and we can prove, that this graph is the relationship between surface area and radius is a squared factor, right? So surface area is proportional to radius squared. That's one thing we saw. We can also show that, or prove that, by saying when we graphed surface area and radius squared, the graph was linear, so therefore they're proportional. So we've proven that. Then we've got to interpret the slope, right? So our slope was about 12.6, which is a good thing because I know the relationship for the surface area of a sphere, and it turns out that it is 4 pi r squared is what it is, and 4 times pi is about 12 point something, okay, which we got a slope of 12.6, so that means that our slope is pretty good. So interpret your slope. In this case, right, we would say that the slope is how much your surface area increases for each unit that your radius squared increases, right? That would be the meaning of that slope. And we would expect it to be 4 times pi, which it is. Interpret your y-intercept, right? In this case, our y-intercept was 0.4. So we would say, hey, look, that represents the amount of surface area for no radius. Then that doesn't make sense. We would expect it to be 0, but that's what we got. And then we would discuss why it might be that we're a little off. X-intercept, if it has one of meaning, you interpret that too. At least always think about it, because it might be something worth talking about. In this case, whatever that value would be, it would represent what the amount of radius you would have to have in order to get 0 surface area. That doesn't really have a whole lot of meaning to me because I would expect it to be 0. So I probably wouldn't talk about that in my lab, but that's something that you can always consider. Sometimes it is useful. Also, the expected end behavior, right? On our graph, it's a squared. It should keep on going, and we would expect that. We mentioned that earlier. So from all this information, you have now learned how to make or to figure out the equation, and it's up to you now to try and do it for your graph. You've got to make the graph and think about your data. It may be a squared function like ours was in our example. It may not. You've got to think and process it. If you find out that it is, cubed, like the relationship should be cubed, then instead of graphing your surface area with radius squared, you would just have to graph surface area with radius cubed, or your value cubed. So you just graph whatever it is that would make it linear. Good luck.